All right, so in true efficient fashion, let's get started. Herb really doesn't need an introduction, but I'm going to give him one anyway. He's the chair of the ISO C++ committee, an unusually prolific author. I'm sure many of you read his books and his blog posts and his articles. So let's have a big hand for Herb Sutter.
Thanks. Well, welcome to day two. So was day one fun? Did you enjoy it?
Yeah.
All right. Thank you, Bjarne, especially for that excellent keynote and all the other speakers. I enjoyed listening to that as much as I'm sure everybody else did. We actually have a special guest this morning. And that special guest, this is in addition to Bjarne, who was our special guest yesterday, and then again later today. Our special guest is that it turns out, this was not planned, but then after we set the dates for this conference, we realized that this is the same month that is the 20th anniversary of C++ at Microsoft. It was in February 1992. How many of you have used C++ 7.0 from Feb 92? Yeah, the audience is getting younger, so there's fewer hands, but still a number of you. By the way, it is good for C++ that the audience is getting younger. But here is our special guest. Remember the days when you used to, in the distant past, have to get a physical DVD? Yeah, those are so old school because we just do internet downloads now, right? But this is the box for Visual C++ 7.0, and before Visual C++ 1.0, this is C++ 7.0, and we actually have some of the original developers, not all of whom are still on the C++ team. The product manager is, none of the developers are, in the room. In fact, right here, if I can get Jan Gray to stand up, please. Could you come down here and show us how heavy this is? Please give him a hand again. Is it more than 1 pound?
44 pounds.
44 pounds.
So
thank you very much.
It's about as much as UPS would deliver in one go, I think.
So for those on the web, it was the UPS delivery limits that said how big that box was going to be. So we're very excited that C++ is still going strong. Now, C++ was supported before then, but through C-front-like mechanisms, through translators that brought it down to C. That was the first C++ native compiler, and native code is still going strong. And now 20 years later, we're very pleased that we're now able to ship Visual C++ beta for Visual C++ 11. Now, this is quite a milestone for us because this is perhaps our biggest release that we've ever done in terms of the number of features put into one release of the compiler. You may have noticed that there are a few industry transitions going on. We never had to support ARM before. This release we had to add ARM support because everybody depends on us to add it. You might have noticed something about these tablet things. It's probably just a flash in the pan. But that required a big re-engineering. It's causing a re-engineering throughout the industry, which we're all benefiting from, and also within Windows. So again, it fell to us to provide the core functionality for that for Win8 tablet apps. Yet another transition that's happening is to heterogeneous and distributed computing. And as a first step toward that, to harness GPU devices and GPU computations, we did C++ AMP, which I'll say a bit more about in a second. And among all that, somehow we found time to also ship, thank you STL, wherever you are, to ship the complete C++ 11 standard library, including threads, atomics, futures, async, and we're very glad to have been able to get that into the product as well. Now, let me just say a couple of words about C++ AMP. In June, I gave a talk about C++ AMP, and it included this slide. Talked about why we were doing it, because we're targeting C++, not C, which other technologies have chosen to do. We want it to be accessible to millions of programmers, not just a small priesthood. We want it to be as little invasive in the language as possible, and we're very glad to have just one language extension and a storage class specifier. To be portable was very important to us, and to deal with not just GPUs, but also multi-core and SSE, cloud computing in the future. Now, when I first gave this, I mentioned that in the initial release, we're focusing only on GPU. That's because I couldn't tell you at the time that we also had technology working as part of Windows 8, that this release, in the beta that you will get in just a few weeks, that you can run code against, you will be able to target not just GPUs for your code, but with that same parallel for each loop, it will automatically fall back. If you don't have a compute class GPU available on your target system, it will dynamically automatically fall back to multi-core and SSE together, vectorized multi-core. So multi-core and vectorized on each core. It's a fallback, and we'll continue to improve that, but that's something we're excited about because it's not just about GPUs. And we also said that we felt this is important, that people not just keep innovation in the C++ space to themselves, but to open it up and to make it available so that others can implement it too. And so we were happy to announce that C++ AMP would be provided under the Microsoft Community Promise as an open specification that any C++ compiler who wants to can implement, and will help them and support them, and for any operating system platform they want, Windows or non-Windows targets, doesn't matter. Make it freely available. But we didn't say when, because we were still working on it. And after months of work, especially with our partners AMD and NVIDIA, we're now pleased to announce that specification is available today for download. You can find the details of the Native Concurrency blog, and we're very grateful to all the help from the experts at AMD, NVIDIA, within Microsoft, and others that have already contributed to that spec, and that will continue to be a living thing. So we're happy to announce that that is available today. If you look back, by the way, this is the last Microsoft-specific slide. The bulk of this talk is all about C++11 portable code on every compiler and platform, and we'll see how we're all doing and what's next for the standard. But one more Microsoft-specific thing. You might have noticed 2 years ago when we shipped Visual C++ 2010, that it contained quite a bit of C++11 work. It was the very first C++ compiler, commercial C++ compiler, to have lambda functions, and our experience there with PPL and using lambdas helped inform the syntax in the standard. And we were among the first, not the first, but among the first to have move, R-value references, auto, decal type, the new style function declaration syntax, null putter, extern template, and a few other things. There's lots more, but we were happy to be able to do that. When we last spoke in September at the Build conference, we released the Visual C++ 11, the next developer preview, so pre-beta. Try it out, see what it is, but a developer preview, which included the complete C++ 11 standard library, including threads, mutexes, async, futures. And we continued to track changes. For instance, the lambda specification changed in C++ 11 between the time we implemented it and the time the standard was published. That's the risk you take when you implement early and in advance of the standard. So we went and we updated lambdas, we updated move semantics and R-value references, which also were revised several times by the standardization committee. But we said we weren't able to add any new C++ 11 language features. We actually tried. We actually planned for it despite all this tsunami. In between these 2 points, notice there was a gap because this is where ARM targeting, the whole tablet revolution, GPU, all happened at the same time. So it was kind of a busy couple of years for the whole industry, and we were in the middle of it. But we tried to also do variadic templates. Turns out it's 2 to 3x harder than everybody thinks when they start. So it's half done, and we ain't going to ship something half done. So we're halfway there. We'll continue to work on it, but it did not fit in this release. And so we said, sadly, we're not going to be able to do any new C++ 11 language features in this release. Fortunately, as you began to hear yesterday, we were able to do a few after all. So I'm pleased to mention that in the beta that ships later this month, in Visual C++, you will have support for range for loop and final and override. It's a start, but you will have that this month from Visual C++. So we're glad to have that, and we think it'll help the way people write portable C++ 11 code. And after that, people will think, gee, you know, you've shipped 11 releases in 20 years. I can do math. And my long division tells me that's approximately a release every 2 years. That's not counting dot releases. That's major releases. So that's great, but does it mean I'm not going to see anything else for another 2 years? And the answer is no, because since last summer, we've been putting in place, working to have an engineering plan to be able to be more agile in our releases. Instead of being necessarily shipped tied to just Visual Studio release cycles, whatever those may be, when you're part of a larger product, that's what happens. What we've decided to do is look at engineering to be able to ship out-of-band releases starting soon after Visual C++ 11 RTMs. So you can expect to see an out-of-band release that's a community tech preview that may include just the command line compiler, but more C++ 11 features soon after Visual C++ 11 ships. And then an out-of-band RTM and be on a faster cadence. We'll give you more details about what faster means as we know ourselves, but this is what we're planning to do because we think it is important to deliver features faster, and in particular the first target of that capability is going to be to deliver C++ 11 language features faster so people can use them on our compiler just like everywhere else. So we're looking forward to that, and if you want to have input onto the order in which we should implement them, we already have a pretty good idea. So we understand C++ 11, we use it ourselves, we know the features that most, we think, need doing. I'm going to mention some of them in my talk today. But just in case that we've got a blind spot and you need something sooner, go to the survey that is live now, and you'll be able to give your input, and that will stay live, as to the relative order in which you would like to see C++ 11 features implemented. We'll do them all, but it's staged releases, and we'll do them in priority order depending on what people need first. I'll come back to that a little bit later, but keep that survey in mind, bit.ly/mscpp11, and that's where we invite input to order those remaining features. So the rest of this talk is about ISO C++ 11 on all platforms. Most of the talk is going to be about how C++ 11 feels like a new language. That's how Bjarne has put it, and he is right, and why that's the case. Then we'll take a look a bit at how C++ adoption is going. How are we learning it? Where are the books? Where are the compilers and the standard libraries? And just look across the industry to see a snapshot of where we are and what's coming up. And then I want to spend a couple of minutes talking about what's next for ISO C++. You may have noticed the theme for day one was C++ 11 today. It's what can I do with C++ 11 today? Variadic templates and R-value references and auto and lambdas. Most of those are supported by most compilers. Every compiler has something the others don't, but there's getting to be a broader availability of core features. But we also want to take a look beyond that, and that's what we'll do near the end. So let me start with this quote from Bjarne. C++ 11 feels like a new language. Wonderful. You may have noticed this. You may have noticed that, wait a minute, if I have auto, if I have lambdas, I just tend to write code differently. And in particular, the way that I like to encapsulate what that means is we have now changed C++ coding style in many ways. The idioms have been updated and sometimes are quite different. And the guidance that prescriptive books like the effective C++ style of book would give have also changed. Many things have stayed the same, but because of these new features, you just naturally do things in a different way. If you look at all the features that are in C++ 11, most of them do not affect style idioms guidance pervasively. They'll do it in whatever area their particular feature is targeted at, but they don't do it pervasively. If you take a look at these specific less than a dozen features, mostly in the language and a couple in the library, I'll make the claim or the observation that these are the features, starting with auto, null pointer, lambdas, range 4, move, and smart pointers, non-member begin and end, that are likely to change just about every 5-line example you will see written. You can pick up any C++ book today, just look at the first piece of code and know, oh, that's the 98 edition. Why? Oh, because you'd use auto, or you'd use braces for initialization, or you'd do something different if you were using C++ 11. So of all of the features that are in C++ 11, all of them are important. We're going to implement all of them. But these are the ones, it seems to me, are the most important because they are the ones that pervasively change the way we code. As soon as we shipped these features as a standards body, we broke every single book on the planet, and we broke every single programmer on the planet. Not that your existing code won't work. Not that your existing code won't work, because we have an excellent backwards compatibility story. But if you're going to use the modern C++, you'll do things differently. So that's one of the reasons I'm going through the exercise of updating Exceptional C++ Guru of the Week, to be using it and show others how it changes the solution. Sometimes it's just changing parens to braces. Sometimes it's adding auto. But often it's the range 4. You'd use a lambda instead, or async, or something else. So let's focus on these ones in particular. And what I want to do is take maybe 2 slides or so, sometimes a couple more, for each one of these features, just to summarize what it is from a user's point of view, and to show you the guidance that we know so far, because we're still learning this, what the guidance we know so far about how to use them effectively. And as we've observed people using these features, what some of the things that they initially trip over, and then once they learn, then they move on. But perhaps we can accelerate everybody by a couple of days just by summarizing the things that people trip over and then never bother encountering again. For auto, I figured, what's the good way to summarize what auto does? And in 1,000 words, I'd say, whatever. Auto means never having to say a type again, at least to declare a variable, except when you really want to commit to a particular type. Now let's think about what this means, because some people find this kind of scary. If you look at the left-hand side of the screen, you'll see the way we used to do things. We declare types. If we want an iterator I have to say, oh, what kind? A map of int to string, : iterator I equals m begin. Or if I want to have just even a double, I have to say double or const double, and then subscript the config file to get a certain value. Or if I want singleton instance, I have to say singleton again, even though it's returning a reference to the same type. That's what I have to do. And it's not the end of the world. It's not that much typing. But isn't it nicer to just be able to say, look, compiler, you know what the type is. Why are you making me say it again? Not only is it convenient to be able to say auto, which, as you'll notice, that you can say plain old auto, which gives you an auto variable, auto const, or const auto, same thing, to say that variable is const, auto ref to make it a reference, because like function parameters, auto strips off top level const and ref. You can do all that, you have all the flexibility. But it's not just a convenience, because sometimes the type that you are trying to say may be difficult or impossible to actually say. The type may actually be unutterable. On the left-hand side, the lower left, you'll see a binder. You have to write, in C++98, if you write bind second greater comma 42, you have to remember what's the type of that. Oh, you look it up because you get a compile error. Cannot convert binder second. Oh, great. Oh, there's an ER in there, I forgot. Okay, so binder second of greater equals blah, blah, blah. And then you move on. It's nice to just say auto. But in that case in the lower left, if you didn't have auto, you could still do it because that code compiles. Heaven help you if you have a lambda function. Or some other unutterable type, maybe compiler generated, maybe something that a library doesn't specify. The standard library has 1 or 2 unspecified types that are implementation defined. So what you want to be able to do is just to say, I just want a variable of this type. So what you should remember about this is there's nothing magical going on. It is exactly what you could write yourself if the type is utterable. It's still statically typed. There's no dynamic typing going on. And it's generic and it's more robust, because think about it. You're not just saving keystrokes. If you say auto and auto x equals f, and if f changes later during maintenance to return, say, a different but compatible type, you used auto. You just recompile, you're done. You don't have to touch that code. Just like if you pass things to templates. In fact, the rules are astonishingly similar to template argument deduction. In fact, they are exactly the same. If you look in the standard to where the rules are, how do I deduce auto? They say, see template argument deduction. It's not just cut and paste it. It is the same set of rules, which gives us something familiar. So the advice that I would give people, and I understand this is controversial because some people are kind of leery about auto. If I say auto, I'm like, what is it really? Look, statically, you know what the type is. IntelliSense is going to show you. You probably know anyway from the library. It's just a convenience. If you want to say the type anyway, go ahead. Bob's your uncle. You can do that. But you don't have to. And my advice to you is to be using auto by default all the time. Just do it. Unless you need a type conversion. If you explicitly want a different type from what that expression is, sure, go ahead and say what that type is. That's where we shouldn't use auto. Now let me give you a couple of examples of that. Let's say you call a library that gives you back something, say a derived star. But you want to hold it by a base star for some reason, because to insulate yourself against the derivedness in case you want to change your code later to use something else, then just say base star equals library call. If you want a conversion from, say it gives you an int and you want a double or something like that, you want a conversion, it gives you something, you say, okay, please convert it to a widget for me. And you declare, I want a widget. Whatever comes out of there, make it a widget, and then you go on to use it a widget. So if you want a type conversion, say so, otherwise use auto. One of the places where this almost never comes up, but for completeness, some of you may be familiar with and use expression libraries. There is one such in the standard called val_array. I think almost nobody uses it, but you'll always find a few. So if you're using that and you say val_array, make val_array 1 plus make val_array 2, what the result of that operator plus is not a val_array. It is an expression template, a proxy handle type, which says, okay, I remember you wanted to add those two val_arrays. You know what, you might say add a few more or multiply. And I can do that more efficiently if I do all of the add, multiply, fuse it, and do it in one operation. So I'm just going to remember that you asked for the add, because maybe you'll do another add, and then I'll remember that in an expression tree. And then when you convert it to a val_array, I'll make it all good. I'll do the computation. And I can get real efficiency gains this way. That's what expression template libraries are for. If you use auto, you will get that supposed to be hidden type, because it will say, yes, I will give you exactly the type that's there. So in those cases, if you want the conversion, in this case, for the first line, you would want to say val_array. That's an example of where you'd want to use a conversion. Now, expression template libraries aren't that widely used, but just keep that case in mind, because that'll save you an hour of compiler diagnostics before you never encounter the problem again anyway. Another example is in, for instance, boost lambda. We have lambda functions in the standard library now, in the standard language now. But before we had that, we had boost lambda, which was an approximation. And you could write things like _1 equals 1. Or f of _1, or things like that. If you capture that with auto, you will get the expression type, not necessarily the type that you intended. And the last example, by the way, what does that last example do? Anybody know? Just shout it out. Initializer list, yes. If you do that, what is the type of z? An array of one in? Integer. It may not be what you think. None of those answers are actually correct. We'll come back to this. But notice there's nothing new here. There are no new language rules. It just says, guess what? You get to write auto, and we'll do exactly the same deduction we already do when you pass template parameters and we deduce their types. Exactly the same rules. Now, let's talk about uniform initialization. We just saw an example, so this is a good time to talk about it. The short version is you'll get used to writing braces much more often than in the past. Consider this C++98 code. If I have a rectangle type, and I have an origin type and an extents type, this is important, all three are types, and I write this thing that looks like a constructor in the first line, what does that actually do? Declare a function. Of course. Even though there are no local functions, and so that doesn't actually mean anything, but don't get me started. So people learn that and they get over it, but yes, it's an icky wart. Let's look at the next line, complex double. What does this do? This one's easy. It's not a trick question. Constructs a complex with e and pi, right? Int a subscript equals 1, 2, 3, 4. Where does that come from? Where have you first seen that? C. What's aggregate initialization, right? It doesn't look like the other ones, but it initializes an array. Well, that's wonderful. Now, what do we tell people to use instead of arrays? Vectors. So of course you want to initialize, you change the array to a vector and the compile breaks, and instead what you do is you write a loop that pushes. In C++11, you just write braces. Almost every kind of initialization syntax is completely uniform. Almost. We've got all the major cases. If you want to initialize a rectangle with a default constructed origin type and a default constructed extents type, you say it. And guess what? It's a variable declaration. Complex double C, same syntax. Array initialization, same syntax. Vector, same syntax. And yes, you could write equals open brace in front of each one of those as well. But it's your style choice. There's not much a semantic difference between them. The equals case, just remember, it's always copy initialization in the language right now, although we keep having that argument every few years. One of these days, I hope Yarna wins. But for now, it's still copy initialization, so there's a notional copy construction. Most compilers just optimize that away. We've done that a long time ago. But here's another one. Today, on the left, I can write int I equals 42. Now, it is true you can write int I, open brace, 42, close brace, semicolon. If you want to do that, more power to you, but I would be embarrassed to tell people to do that. Just say int I equals 42. It still works. It's fat-free. It just works. And in particular, with auto, if you have auto, it just seems natural to say auto x equals begin v, plus you better say it that way, because if you try to use the braces, the wrong thing will happen in some cases. Actually, in pretty much all cases. Now, there's one other cool thing in initializer lists, which is one of the reasons that you saw me mention uniform initialization and initializer lists as one of the first features I think we ought to do once we get all the tablet and ARM stuff and AMP stuff out the door, is because you can just create a temporary on the fly using brace initialization syntax. If I have a drawRect function that takes a rectangle, I don't have a rectangle object, I could just make one on the lower left today on the fly. Just construct a temporary and pass it. But the compiler knows what drawRect takes. Here, just pass it one of those. You know the type to construct. Nike, just do it. And that's the lower right syntax. Another form of whatever. But in this case, I would call it just do it. So we're still learning the right guidance to use even for basic features like this, because frankly, some things in the standard don't have much commercial usage experience. Almost everything has an implementation, but it may just be a research implementation to show it can be done. The standard tends to be well ahead of existing practice, not as much as C++98 was, but still maybe a couple of years, so we're still learning. But here is the current consensus understanding guidance that we think is the right guidance to give. And so we've discussed this on the reflectors. This is actually almost cut and pasted from one of Bjarne's emails from the standards reflector. So questions over to this corner. But I agree. Just use braces unless you have a reason not to. And there's three major ones that I can think of. The first is for convenience. If it doesn't seem right to initialize a variable with braces, you're just not used to it, you just like to say equals 42, just do it. It's perfectly fine. There's nothing wrong with that. Now, the second case is, and by the way, in that first case, you also want to use that syntax with auto. I'll come back to that at the end of the slide. The second case is, what if you have a certain type which takes an initializer list, because initializer list is a standard type now, and you can have a constructor that takes one, and that's what gives your type access to all these wonderful initialization semantics, right? What if you overload your constructor? You have an initializer list constructor, but you also say have a constructor that takes an int. O like stood vector does. Well, the trouble is that if you have such a case, if you write, for example, vector int v brace 100 brace, remember that brace is initializer list. We always do expressions first in isolation. We're not context dependent. There's nothing context dependent in the language. That's the same reason we don't overload on return type, right? You don't decide what to do just based on the context of where you're called. Every expression can be looked at in isolation. This initializer list expression has types to the initializer list. If you pass it to vector, you will get a vector with one element that has the value 100. If you pass it to the vector constructor. If you wanted the vector constructor that says, give me 100 default constructed elements, so the size is 100, use params to opt out and use the non-initializer list constructors. So that's another case where sometimes you may not want to use the brace syntax. Normally use it, but here are two cases where you want to use the params. One last case. If you're writing an auto variable and you don't want it to capture an initializer list, don't use braces. use the equal sign. Same example we already saw in the previous slide. But here's Richard Smith's example from the committee reflectors. If you say auto w paren n paren, because that auto w is an int. If you say equals n, it's an int. It's always been that way, no change. But if you say brace, with or without the equals, it's an initializer list, and auto will happily capture exactly the type that you gave it. So just be aware of that. But mostly, except for the first one, convenience, which is easy to remember, it's just I kind of prefer the equal syntax, mostly these are corner cases that you'll rarely come across, and once you learn them, you'll never stumble over it again. Use the brace initialization unless you have a reason not to. Now let's talk about the range-based for loop, which is one of the things we're happy to add that's in the beta of Visual C++ that's coming out in a few weeks that you'll be able to play with in our compiler too, as well as GCC and Clang and others. The range-based for loop is really nice. Here's a nice summary. I thought I'll just paste the Wikipedia entry because it pretty much says in one sentence what it is. And it also points out that one or two other languages have discovered this a long time ago. Notable languages at the end without for each are C and C++ prior to C11. So basically, since that doesn't exist anymore, we're all going to a C++11 world. It's just C. Actually, you know what occurs to me? I never thought of it. Maybe we should propose range 4 for C. Well, no, they're done, so maybe in a few years. You didn't hear that. So let's take a look at what this means for you. How many of you have enjoyed writing code like the left-hand side? No. I said enjoyed. Okay, that's better. It's way too many hands here. So we're very glad. And John, you hated this so much that you implemented the range 4 in the compiler. So thank you again for doing that. Thank you for SCL for testing it and QAing it. And isn't it so much easier to just say for auto d:\v, which, by the way, apart from the auto, is Java syntax, but Java didn't invent it. It just happens to be a convenient syntax. And certain languages don't really have auto quite the same way. So if I just say for auto dv, notice that that right-hand column is a lot slimmer than the left-hand column. But it gets better. Wait, because in the lower left, you'll notice if I sort a vector, let's say I have a vector v, because if you see a variable named v, it's a vector, right? It's got it. But it's not Hungarian. So sort v.begin v_end. Oh, but if you have an array, which you should use vector anyway, but let's say you have a smelly old array, sort &address sub 0, comma, &address sub 0 plus size of a divided by size of a sub 0 paren semicolon. And even if you've been doing this for 20 years, I posted this and forgot the divided by size of a sub 0. Fortunately, 10 people immediately jumped on and said, he doesn't even know C++, and I could fix it. Because we forget, right? Because usually we have a macro for this because it comes up. Well, isn't it so nice that in the standard, we can say sort begin of v, end of v, and sort begin of a, end of a, and it's consistent and just works. That's what we should do. So notice I put range 4 and I put begin and end together because for range 4, you should just use it. There's just no reason not to if it's appropriate for the loop that you're writing. If that's what you intend to write, use it. Remember, you're declaring intent better also. The person who reads your loop knows without looking through the body of your loop that you're not going to be squirreling away some extra increment of the iterator or backtrack and visit elements twice or skip elements. You know you're going to visit this loop body once per element in whatever you're iterating over. Remember that if you want access to the actual object in the collection that you're iterating over, use auto ref. Yeah, you can type something longer than auto, but we already said don't do that. You know, why bother? So do auto ref because that will give you a reference in. If you say auto, that's fine if it's like a built-in type, an int or a double, and you don't want to modify the original. Fine, do that. But most of the time you'll want to use auto ref if you want to avoid a copy. Also, there is a slight syntactic but major semantic difference between member begin and end and non-member begin and end. v.begin paren only looks like a slight arrangement of begin paren v paren. Like you save a whole character, it's great. But the semantic difference is actually quite profound. because the non-member ones can be overloaded. They can be looked up through argument-dependent lookup. It means you can use the same type and say the same for each begin and end, or whatever it is you want to write, for any container type, even if it does not have begin and end member functions, as long as you can provide the non-members that do something equivalent. The reason that the lower right example works for arrays is because the standard already did exactly that for arrays. They provided an overload where you can say begin of array, end of array, and it will do the right thing. In C++CX, so if you're doing WinRT, Windows 8 Metro tablet apps in our current compiler that's going to be in beta later this month, we overloaded non-member begin and end per the standard for the WinRT collections so that you can iterate over them with exactly the same syntax. No difference from iterating over a standard vector, character for character, identical code. If you have a container type, one that you wrote in-house, one that you get from a third party who may still not have gotten this whole STL thing, but it's a container and it works pretty much like you're used to containers working, go and define your own non-member begin and end and use it to get this syntax. By the way, the range 4 will pick it up. And so all of this is nicely integrated. It gives you a nice integration point to take non-STL-like libraries and just seamlessly integrate them with the standard. So although there's only a very slight syntactic difference here, there is a big semantic difference, and you should definitely use the non-member versions of begin and end. Everything will just work a lot more of the time. Now, you might remember that on containers you get .cbegin and .cend. Those give you const iterators, right? Now, this only comes up if you have a non-const container object and you want the const iterator. Because if you have a const vector and you say .begin, it already gives you a const iterator. It's already overloaded for that. But if I have just a plain old non-const vector and I really want a const iterator, I just want to declare my intent not to modify and be a good person, that's where you say .cbegin. Turns out we kind of forgot to implement cbegin and cend non-member versions. Don't worry, there's an issue for that. And C++ post 11 is certain to get that, as certain as anything is. But I'm willing to say is certain to get that. Several of us will make sure that happens. In the meantime, just write it yourself. Here's the code, cut and paste. And the standardized version, might have a few tweaks here and there. Bob's your uncle, just use this. It'll be fine. You won't even be able to tell the difference. And then you can use the standard ones and get rid of those 2 lines when it's available. So use this for now. You have no excuse not to use non-member begin and end and non-member cbegin, cend. Use them. The next C++ 11 feature that changes many 10-line code examples in books just by itself is smart pointers. Specifically shared putter, weak putter, unique putter, and that other one that doesn't exist anymore. And the way I like to characterize this, to summarize what this is about, C++ is already type safe. If you ignore the reinterpret casts and reinterpret unions, that kind of thing, C++ is already a statically and strongly typed and type-safe language. It is, however, not memory safe, which is actually, depending on who you argue with theoretically over dinner, is a requirement for being type-safe because you don't want to have dangling pointers. That's the usual extra piece of the definition. We've always said, oh yeah, just have a smart pointer. That kind of falls down when you say, but oh well, there's no standard one. And so now that we have standard smart pointers, it gives us standard and portable memory safety when you use it. No more dangling pointers. In fact, most authors will tell you, not all, but most will tell you, you should just never write naked new and delete again. Which is pretty profound because, well, isn't that one of the basic language features? Doesn't every language have new and delete? Make unique and make shared will make you objects. A bit more about make unique later. Hold that thought. So notice in C++98 we'd say widget star pw equals new widget, and then later on we delete it, which is fine unless there's an exception. Or there's a control path where you do an if-else and you have to remember to delete it once on each branch, but not once again at the end. That could be a double delete. And am I exception safe? My head hurts. Let's use a smart pointer. By the way, if you have a smart pointer, you don't even need to say shared putter. Please do not say shared putter of widget equals or paren new widget. Don't do that. Why not? because make shared is shorter and it's more efficient. STL talked about that a bit yesterday. STL the person, not the library. This is very confusing all the time here. But just use make shared. You say the type, you pass a constructor parameters if there are any, and then use auto to capture it. You never even need to say a shared putter in this kind of case. And by the way, there's no delete. You can't get it wrong. It will continue to track ownership. And if you don't need the sharedness, by all means use unique putter, because that's the one, don't pay for what you don't use. So use unique putter when appropriate. Use make shared and shared putter, and I show that one here primarily because make shared is already in the standard. But what about unique putter? If I have, say, a case I have unique ownership, a node owns its children, unique putter is the natural way to spell that. If I have a child node owned by its parent and it needs a pointer back to the parent node, what do you use? That is perfectly safe. Raw pointer. It seems hard to say that after and it's safe, right? Why is the raw pointer perfectly safe here? You're never going to delete it. It doesn't own anything. It's a non-owning. It only refers, it does not own, and it refers to something that is guaranteed to outlive it. True, there's nothing in the language that actually says so, but you know by construction, the parent owns its children. I said so with unique putter. The child can have a raw pointer to its parent. It's perfectly safe because it observes it does not own. Owning raw pointers are evil, smelly, and should be just taken away and riffed, but replaced with owning smart pointers. But non-owning pointers and references that refer to things that are guaranteed to outlive, perfectly fine. So use shared putter to express shared ownership. And if you have a cycle or you want to break a cycle, for example, or express optionality, if you're implementing a cache, say, then use weak putter. And use make shared and make unique to create objects. You'll notice a namespace qualification on make unique. And prefer never to write raw new or raw delete. Now, it's true, some library you call may new up something, and then you put it in a unique putter, but at least you didn't call new. And finally, a non-owning star or ref is fine if it's for observation, not ownership, and it's guaranteed to outlive. Now, I mentioned make unique. So here's another oversight in the standard, just an oversight. It's not part of ISO C++ yet. You can say make shared of widget, but you can't say make unique of widget. This will be fixed. Again, we'll make sure that it gets there. For now, write it yourself. Here's the code. You might notice that this uses variadic templates and just forwards arguments. Is very nice. And if you want a longer discussion, see Guru of the Week number 102 that I wrote a few weeks ago, and it talks about this in a bit more detail. Now, there's one more thing to be said about smart pointers. Smart pointers have got a very bad rep for being slow, especially reference-counted shared pointers, because they've got to have a reference count. That's how they manage memory. You save a lot of time later in doing garbage collection because you're not creating garbage, you're keeping track accurately. But there is overhead to those reference counts, right? What happens if you write the code at the bottom of the screen? You get an atomic increment decrement, which by far dominates the cost of copying that parameter, because it has to be concurrency safe, an atomic increment decrement. You almost never want to pass. In fact, I would say never. I don't know of a good case where you would want to pass a shared putter by value as a function parameter. So what do? It's easy. Just do what you're doing now. Shared putters and unique putters are largely not for parameters. On the stack, as it says at the top by default, use star and ref exactly using the same rules you already know. By the way, for reference, it might now be our value reference, but the same rules apply. Now, sometimes you will want to use, let me back up. The nice thing about saying it that way is you don't care if the widget is being held by shared putter, if it's being held by unique putter or something else, some other counted pointer, or whatever its lifetime management policy is. You're agnostic to it. After all you want is a widget. You don't care or need to know. You want to be insulated from the knowledge of who owns it and how its lifetime is managed. But if you want to participate in lifetime management, if you want to somewhere store a copy of that, then you may want to commit to a particular smart pointer type, in particular shared pointer if you want to store a copy. That's when you say, okay, give me a shared pointer, but notice not by value. It would work if you did it by value. It would be needlessly slow. You do it by const reference. Const reference. Now, you might notice a little thing that said, see next 2 slides. So let's see why it should be constant reference. This came up, by the way, when we were doing C++ CX and we were doing the hat, which is basically a compiler built-in and heavily optimized shared putter, because the same issues come up. So you learn a lot about parameter passing. The example on this screen and on the next slide, notice I'm going back and forth just to show you the example is pretty much the same, but let's start with this one. If you have a function that takes a non-const reference to shared putter, and maybe other parameters, or it has access to other things, the first 2 lines of code show how you might call that. You have some sort of global, doesn't mean file static, it could just be on the heap somewhere, some non-local shared putter, g_spw. Then I call f with gspw, and in this case, there are other ways you could get the aliasing, but for convenience, I'm just going to pass in a dereference to that as well. Pass in a widget, which happens to be an alias, a reference to the widget that's owned by that shared putter, okay? Inside f, everything's going happily along, and then I hit the line that says spw equals some other widget. I'm assigning to my parameter, because it's not const. Remember, last slide I said make it const, but if you make it non-const, you can do this. This is an oops. It might work. That line will definitely work. The assignment to the SPW will definitely work. But if that was the last owning reference, if ref count had been 1 at that point, what will that do to the original object that SPW pointed to?
Delete it.
Delete it. And what are you going to try to draw on in the next line?
What you just deleted.
What you just deleted. Isn't it wonderful? So the good news is there's a really easy solution to this. Just don't pass parameters by reference to non-const. Just say const reference. If you're going to say reference, say const reference. The flip side of this is there's 2 sides. If you have a global thing and you pass it by reference, you might modify, reseat the copy, or the reference rather, the parameter. You can prevent that by saying const. But now what if you reseat the global? So same code, but now inside the function, I call spw draw, happily draws the thing. Then I say global spw, so the non-local one maybe on the heap somewhere. I reseat it to some other widget. If that was the last reference, we delete the object, the original one. I then say w.draw, which could be dangling. But even if I don't have aliasing, notice if I just try to use spw itself, the smart pointer again, the first spw draw line and the second one may use different objects. That may not be what you expected. There is no nice const way, generally, to prevent this unless you can arrange to make the global one const. So the solution here is don't do that. Now let's talk about move semantics. So basically, just summarizing that, you generally don't, shared pointers are great and unique pointers, but you generally do not want to pass them as parameters. Just use normal pointers and references for parameters. And it's efficient, fast, and has the same meaning as it always has. Move semantics. It was described yesterday, it summarized very nicely, that I get the efficiency of reference types with the predictability of value types and the semantics of value types. In particular, I don't have to worry about pointers, which could dangle. I don't have to worry about lifetimes because I know where values exist. This is really important because it lets C++, which is all about value types that you copy and so forth, it lets you get the same efficiency as passing an object star in some other language. On the left-hand side, we can see how this changes the guidance we give. It changes the way we write our APIs. If I want to have a function that is a factory, it makes loads something from disk, makes a big vector. What do I do today? Do I return by value? That's one of the first things you learn is don't return by value. Why would you not return a 1,000,000 element vector by value in C++ 98? Who wants that memory spike and needless copy? That's a pessimization. You just don't do that. I had to say in C++ 98, because in C++11 that is exactly what you should do, is return by value. We'll come to that. So what do you do in C++98? Well, you may say, oh, I'll just new up a vector and return a pointer. Fine, but now somebody has to know to make sure it doesn't dangle. What if they ignore the return value? Oops. So you might want to actually return a smart pointer or something. That's the second option. But isn't it kind of odd to see shared putter of vector of int, but that's really what you need in order to return something safely? Or you take an out parameter. You say, okay, caller, you give me a vector and I'll fill it in. But that's not the same pattern. That's caller allocated out parameter. What if you really want callee allocated, a factory callee allocated out? In C++11, return by value is your friend. And because of move semantics that will just steal the guts, since we know this object's going to be going away, won't be using it again, we'll steal the guts and you'll be just as efficient. It is important to notice this is not an optimization in the sense that you hope the compiler will do it. It is required by the standard that this happen. So it's not like, let me look at the latest chart of whether my compiler implements the return value optimization. No, it's required to do this, and you can rely on it. The right way to think about move is that it is an optimization of copy. That is the right way to think about it. It happens to do a few other things, such as perfect forwarding. It's an enabler for that. But if you think about move semantics itself, don't confuse yourself, it's about optimizing copies, about letting value types have some of the efficiency of reference types when you know it's going away anyway and I can just steal the guts. Use return by value to express callee allocated out. Now notice, one of the first things people might do is return an R-value reference. So now remember this C++98 code. You would never return a pointer or a reference to a local object, right? On purpose. So don't return an R-value reference. It's still a reference, right? And STL has noticed that, and thank you for pointing this out on the reflectors, this is a fairly common first-timer's mistake that then you learn and you get over. But generally, unless you really, really know what you're doing and are trying to do something very advanced, you don't return R-value references generally. Just return by value. The nice thing about that code in the lower left is it's natural, it's clean, it's safe, and it's really fast. There's no pessimization built into it at all. Lambda functions can fill a talk. I have a 2-hour video to prove it. The short version in one slide is you can pass code around like an object. It works pervasively all over the place. Here is where you can find the longer version of the talk. But basically, you could take your handwritten loops, just make them algorithm calls. This feature by itself makes the STL algorithms, easily 100x more usable and going to be more heavily used. And that is only a small bit of what lambdas do to the language, because they can be used in so many other places. Very small one-slide example. If you write a new algorithm, like for each nth, it's almost as good as having written a new loop in the language. I mean, how cool is that? Because anybody can just call for each nth and pass my vector, pass stepwise, step 3, and a lambda as to what to do. That's pretty sweet, and I didn't have to wait for my compiler writer to implement a new kind of for loop in the language that did step. And parallel algorithms like PPL and TBB take advantage of this heavily, and so does C++ AMP. Now again, remember the same as we just said, you would never purposely return a reference or a pointer to a local object, right? Because you're returning something that's guaranteed to dangle because the local goes out of scope. Well then, same way, be careful of where you capture references to locals. In the middle bottom example, if you capture a reference to a local in a lambda and return the lambda, look, that's returning a reference. It's not magical. People might at first say, oh, lambdas are so hard. No, it's just same old, same old. It's returning a reference, that's all. And another example on the bottom right is calling async with a lambda, because that's also taking a reference and putting it somewhere outside the local scope. Same thing would be if you wrote a reference or a pointer or a lambda containing one of those to a heap location. So capture by value is a very good thing to use unless you need capture by reference and you know you're going to stay local. So the summary here is that with C++11, modern C++ code is clean, it is safe, it is fast. It is as clean and as safe, line for line in readability, as any other modern language. And Bjarne asked me to include the sub-bullet, when used in a modern style. We are highly backward compatible. You can write code that is C, that compiles C++, and call it C++, and say, look how awful that is. That's a lie. That is not modern C++. It's using backward compatibility. That's writing C or C with classes. You use C++11, you'll probably never see new or delete again. You'll have efficiency you never had before because C++ was always fast. It is now even faster thanks to move semantics, const expr, and a few other features that take what was already there and then takes it to the next level to make it better still. That's a summary in a nutshell of most of the features that really make C++11 feel like a new language. Almost every 5-line piece of code is going to use one or more of those features. So we just broke all the books. So let's now take a look at our adoption scorecard. We also broke all the compilers and we broke all the programmers. So now how are we doing? We are at a stage now where the entire industry is absorbing C++11. That includes you. That's why we're having this conference, because there's this vacuum of knowledge and we have to have the books, the conferences, the compilers, the libraries catch up. And so we thought, well, we've got to have this. We'll videotape everything, make it available on demand, and at least now we're starting to build some of the information that you can point people to learn about modern C++. Now, as I say, the world is still in the early stages of gaining field experience with things. That includes everybody. Do not think that the ivory tower WG21 geeks who know the standard well and can quote you chapter and verse of Clause 14 templates, do not think that they understand C++11 entirely. We're all learning all the interactions. Now, having said that, I'm not saying this to scare anybody. The C++11 standard, I've been at both ends of this. The C++11 standard is of higher quality than the C++98 standard, which was pretty good. And C++11 is of uniformly higher quality. It is also not as far out in front because it took 3 or 4 years, minus export template and exception specifications, which are now gone. It still took 3 or 4 years for compilers to catch up after 98 shipped, C++, which was finished in 97. So it still took about that long. We'll talk in a second about how long it'll be this time. Probably a lot less until we catch up. But we're still learning because it's high quality. But when we actually use these things in the field on million line of code projects, then we start seeing the corner cases. And that's where we're going to fix those and make sure that we issue a core addendum or something appropriate like that to do an update to the standard. And in the meantime, compiler vendors will support you and they'll make sure your code does the right thing. Let me give an example of this just to illustrate that we really are still learning this by picking on one of the oldest, not the oldest, but one of the oldest C++11 features. Move semantics, our value references we just talked about. When were they first proposed? 2002. By the way, it's interesting when you think about how long ago that is. That was a year into the C++OX process already. The very first meeting, by the way, historical curiosity, the very first meeting at which C++OX was discussed was in this room as we were hosted on the Microsoft campus. I was not there then. There's a long story there. But we all met together. We started talking about what's next, what shall we do, and started generating ideas for papers that at the next meeting in Curacao we started to look at. And that's some time ago. It was 1 month after 9/11. It was the first standard meeting in this era. And now here we are in 2011, so looking at the first move initial proposal, 9 years after that, the same primary author, Howard Hinnant, super smart guy at MetroWorks and now at Apple, says as follows, I quote, "We are still in an infancy stage with regard to having a good working knowledge of how to use our value references. I would very much like us to consider field experience before we make decisions about how to fix corner cases." It's not meant to be scary, and I show you this in full disclosure, knowing that a few people on the internet are going to take it out of context and say, oh, look, C++11 is broken. No, that's not true at all. But we do have to acknowledge we're all learning this together. Good news is, your book authors are learning it too, and we're all in this together, and this is a great start in understanding. We'll fix a few little corner cases like we're missing cBegin and cEnd, we're missing make unique, that'll all come back. But let's talk about where we are with conformance. So first of all, with implementations. Right now, in early 2012, several of the major compilers have complete or nearly complete C++11 library implementations. So our beta, which is coming out in a couple of weeks, and also the developer preview already for that matter last year, had the full C++11 library. And GCC, I believe, has nearly all of it or all of it, although I know at least threads and mutexes last time I looked, and atomics and the concurrency stuff didn't work on all platforms, but we're all getting there. And so I'm hopeful that by the end of this year, all major compilers may actually be there. At least there are several implementations of the library part. And that's a good thing because it lets us write portable code with atomics, futures, make shared, and all of those wonderful things. On the language side, I'm not making any product announcements for other people, nor am I talking about my own product. This is just an observation as somebody in the standards process who talks over a beer and asks, like, how's it going to all the major compiler vendors? It looks to me like it's likely that we'll see the very first reasonably fully conforming C++11 compiler sometime next year, maybe early next year, but sometime next year. And we're all working at it. Everybody's got something the others don't. We're all moving forward. But that's not too bad. That's just in about another year. And most of the things that we talked about as being the core of what makes C++11 feel like a new language, most of those are already portably available. So everybody's prioritizing and doing the important stuff first. And we should actually be reasonably complete, at least for one or two implementations. There's only 4 major ones now in 2013, which is good. Now, what about learning? All of the major books are under revision right now. So I know from talking with Barb Mu, who is the current maintainer and writer of C++ Primer. That's the one that Stan Lippin began many years ago, and Barb Mu was the primary author on 4th edition. She's hard at work on 5th edition. It looks great. I just love what she's done with the layout of the book, and I'm glad to have seen proofs just a couple of days ago. That is on track to be done in August. So Pearson Education, Addison Wesley, who is doing all of these books, would like you to know that yes, we said August and it actually looks likely, so that's a good thing. That's one of the key books we need because we need to have the major books in place for people to learn this stuff. Primer is one of those. Probably the most important one of those, and I'm putting these in date order, is Bjarne's book, The C++ Programming Language. I know he's been hard at work for the past year and is getting very close to done. That looks like it's late 2012, so that'll be later this year that 4th edition should be available. You may notice that Bjarne has also written another important book, Programming Principles and Practice Using C++, which is a book for people who don't know how to program. It is not just a first C++ book. It is a first programming book that, wait for it, uses C++ as its language to teach new programmers. Just that concept would send people running to the exits years ago. And it works well already in C++ 98, and just wait for the next edition. Roughly, not putting any words in his mouth, but you know, it's the size of the work. It wouldn't be surprising if it took roughly a year, and so maybe late 2013, so we'll see how that goes. We need the C++ programming language first, but that first introductory book is a very important one, and I'm sure that as soon as possible, he'll then switch to that. Nice priority order. The 4th one is we need the standard second book to read. Like once you've learned the basic rules and you've got the reference, so the intro and the reference, the standard second book you read for style guidance has historically been Scott Meyer's Effective C++. And there are no firm dates. It hasn't planned starting work on it yet, but looks like that might be in 2013, maybe in 2014. If you want that done sooner, he's going to hate me for saying this. If you want that done sooner, make internet petitions, deluge his email inbox, and let him know that you are ready to buy that book. We all need it, and I think he'll do it anyway. But you know, a little pressure never hurts. Sorry, Scott. I seem to always abuse you in my talks. I don't know why. We like your book. We want it. Please, please, please give it to us. Now, C++ coding standards is another one that people say, oh, we need that one right away. No. Remember what I said on the previous slide? We're still learning what C++11 is. Effective C++ can be written once we learn that. You know, there's a reason Scott hasn't written it yet, hasn't started writing it yet, is because we are still learning what the guidance is. He is professional enough not to ship the wild, fanciful ideas that aren't proven yet. So we need a little bit of time, and then he'll get going on it. But C++ coding standards is by far the most thoroughly reviewed by a who's who of anybody who is anybody in C++ consensus guidance on here is what is utterly non-controversial. You know, you might have with the NVI idiom or with one other thing, you might have one or two people who wonder about that. But in general, it is completely non-controversial, best practices that is established. And we just will not be in a position to write that for another couple of years. We're going to get there, but that is the one to write last, because you need to know exactly what the right thing to say is. Because people are going to take that book and adopt it as a corporate coding guideline and then add to it. You want to make sure you're leading them down the right path and you're certain of it. So Effective C++ is going to give you good stuff, and then that one soon after. So what's next for ISO C++? My suggestion for what we should do with the next round of standardization on the language side, we have a few things we can fix, but it would be great if we could keep ourselves to small things. Now the problem is how do you define small things? My elephant is small. I want my elephant in the standard. I'm not making this up. That is almost, you change that to another noun that I won't say, but that's how everybody feels about their feature. It looks small to me. It's cuddly too. Want to pet it? But that we can't afford to do that. We just broke the world of programmers of books, and my own personal feeling is we better not do that again for maybe another 5 years. Let everybody catch up. We just looked at how long it's going to take books and compilers to catch up. It doesn't mean we can't do anything, though. But let's not do anything that would change, again, style, idiom, and guidance that would be obvious in any 5-line example. Let's not immediately break the books again, because we don't need to. C++11 is very good. The things that most needed are there. We can call it done for a while. Now, what can we do still? An example of a small feature is I would love to see features that reduce the use of macros. That's not breaking guidance about the language because macros aren't in the language. Yes, I'm splitting hairs, but I want to split that one. In particular, one of the big pervasive uses of macros is include guards. If we could have even just pound once, include once, which is currently being actively having initial discussion on the reflectors, or potentially even a module system that looks like it will actually work and be complete, that would be an excellent way to remove those uses of macros. Another thing I would like to see us reduce is template metaprogramming. Template metaprogramming is great because it shows how powerful and Turing-complete C++ is, what you can do, whether or not you should, and largely what library writers can do for you that you can be mostly insulated from until you get the template barf. But generally, there's power there. But the main value in it is it shows how hard people are willing to work to simulate a missing feature. Boost Lambda is a great example of this. Because Boost Lambda, its primary contribution was to demonstrate by showing the best possible C++98 Lambda library why it needed to be a language feature. That is not at all a diss against Boost Lambda. I recommended it long before we had a language replacement. Now I recommend the language replacement. But it had limitations, it had gotchas, it thoroughly explored. Here is the shape of the boundary of how far you can get. You can't go over there. You can get most of the way this direction. Forget about member functions. Well, we'll throw in some binders into that swamp. You see what the shape of it is, and it motivates that you need a language feature. The uses of template metaprogramming today are excellent for showing how hard people are willing to work for maybe a couple of important things that we could give them that they shouldn't need to write metaprograms for. Oh, look, they're trying to write this metaprogram. They're making 3 different types. They have to know what sphinx means. You probably do, but you don't. That's an indication of what you don't want to even know about. And specialization in end cases, because I don't have static if. Well, let's think about static if. It's interesting because I invited Andre in particular from his experience in D and Walter Bright with static if in that language. I invited them, would you please propose it for C++? And they graciously agreed, and so they wrote a paper, and it turns out that someone else independently, Walter Brown, wrote a paper also for the Kona meeting, will be out in 3 days, proposing static if that was virtually identical and also based on Dee's experience. We have lots to learn from other languages. We can use that in C++ and get all that benefit. I also thought this was important enough to invite Andre to give a talk about it this afternoon. So he graciously agreed and made up a brand new talk to talk about static if. So we'll drill into that more this afternoon. So reducing template metaprogramming doesn't change guidance for 5-line pieces of source code. It's bringing into the language stuff that is just too hard, is really outside what people can reasonably write today. A third example of usability improvements that doesn't break guidance, it doesn't really break the examples in the literature, but it makes it much easier to write the code that you need to write, is polymorphic lambdas. I am glad to see there are several committee members beating down the door to be the first to write polymorphic lambdas proposals. And in particular, the idea is that instead of committing to a type name, you can say auto for the parameter, which means the lambda operator, function call operator, has to be a template. Think about it, and then we deduce it. It makes certain kinds of code much easier to write and enables things you couldn't write before. By the way, that middle line, auto reference X, that's the basic idea to sketch out, the basic idea of what polymorphic lambdas would be. Once you've got that, why not allow omitting the type and just by default making it autoref? And oh, by the way, if you're only going to return a single expression, why not just get rid of the return and the semicolon? We're not far away from a very clean syntax that's even better than the clean syntax we already have. So I am very hopeful that we're going to see things along those lines in the near future. And we can do all of these things without breaking the books again and still delivering real value in the language. The key thing is defining what is a small feature. But now I have a question for everybody in the audience. What is standard C++'s biggest weakness? Oh, count me the ways. Who wants to start? Just shout it out.
Not
Eric.
enough libraries.
Not enough libraries. Okay, anybody else? Let me hear from you. Who said messaging? Wave. Okay, messaging. What else do I have?
Reflection.
What's that?
Reflection.
Reflection. Okay, what else are we missing?
Header tree. UI toolkit.
UI toolkit.
It's difficult to learn.
Hard to learn.
Precompiled headers.
Precompiled headers, you'd like that in the standard?
Compilation time.
Compilation time, sorry.
Too much to try to learn. Too big.
Too big in the language. Okay, what else? Template barf, okay. Also known as template spew, okay.
Lack of modularity.
Lack of modularity. By the way, template barf, we have a Clang talk. Watch for that coming up next.
Lack of a good implementation.
Lack of a good implementation. Okay, we're working on that, but that's what we're lacking, okay?
Marketing.
Marketing, okay. Anything else? What's standard C++ missing? Nobody's talking language features so much.
Partial classes are working well with tool-generated code.
Partial classes, tool-generated code. By the way, that's another example of something that can be added and proposed without breaking the existing model in the books. I'm this close to writing the proposal on that because we actually did partial classes in our implementation for C++ CX. So we have some guidance there that we'd like to contribute. Yes?
Syntax.
Syntax.
I'd say there's lots of ways for beginners to shoot themselves in the foot.
Help with pointing the rifle at your toe. All right. Walter.
Deprecation of obsolete features.
Deprecating obsolete features. So you'd like to see us actually get rid of some things.
Yeah, like
But we did that with export. But trigraphs you'd like to get rid of? Okay. Let me take one or two others. Yes. Closures? Okay. So we have lambdas that capture nothing, but maybe something even better for that. Okay.
Very slow iterative development time.
Very slow iterative development time. You must have something you hate about C++.
Build model.
Build model. Modules. Okay.
Deletion of all forward declaration pointers.
Say it again.
Delete forward declared pointers.
Deleting forward declared pointers. Okay, there are some cases where you can do that, but okay, I see where you're going. One more.
Interoperability with languages that are not named C.
So for those of you, the last one was with languages that are not named C. Okay. So we have a lot of interesting things that people would like. I'm going to argue that standard C++'s biggest weakness is not its syntax. Yeah, there's a few extra words here and there. I'd like to not have to say the word template and just put the parameters after the class name. It's not a big deal. It is not its lack of safety, because we have the ++ replacements for the C bits. We have memory safety now with shared pointers. Some people will say it's a certain missing language feature. I cannot think of an important missing language feature that could be called, that rises to the level of being called C++'s biggest weakness now that we have C++11. There's nothing that big. There's more things we can do, but we have a really good language and a very flexible and powerful language. But some of you said a GUI toolkit or libraries or something like that. So let me motivate that, because if you look at what portable standard C++ means. Portable C++, a piece of code I can write and be guaranteed will work on every platform. Today, on the language side means C++98 language, and on the library side, C++98 standard library. That is all of portable C++ for about the past decade. We have a bit more in some community libraries that are popular, like Boost, but you can't rely on them being shipped with every compiler implementation, supported by the compiler vendor. If you want to write portable C++, if you want to write a book about C++ that's intended for all C++ programmers, you have to use only what's in here, the C++98 standard language and library. Now, compare its size. What I actually did is I went through, and this is rough, because there's more to size than just page count or word count or number of types in a library. But I use those as proxies to estimate by area, to scale, roughly the size of C++98 on the language side and library side. So you'll see that the library was a bit more than the language. The standard page count was slightly more than half about the library. But how does that compare to, say, C? Well, the first C standard, if you do the same kind of exercise, and this is using rough proxies like page count and word count and types, the C90 standard library was smaller than the language. That's why anytime you showed up at a new job, you had to either bring your diskette with your own doubly linked list or write it again, and you got really good at previous and next pointers and splicing. Remember those days? We've all done it if we were there. Because the standard library was so small. I have F open, F close, but no data structures, not those kinds of things. Now, that was at least better than KNR, because KNR, which was where all things started, and where Dennis did a wonderful, wonderful job, was an even smaller, cleaner core, because he was doing something nobody said could be done, which was write a clean and portable systems programming language that was high level, that would give systems performance and efficiency across a broad range of architectures, which varied even more than today. But C++98 is bigger than those. If you look at what happened in C, let's go off on that track for a second. In the C99 time frame, there were more language extensions added, but especially more libraries, but you mostly only cared about those libraries, many of them, not all, but many, if you were into specialty numerics work. And then C11, which also just shipped, added very few extra words to its specification for the language and some to its library, and they were almost all for concurrency. Memory model on the language side and threads, atomics, and those kinds of things, threads and mutexes and atomics on the library side, where they largely followed and are largely compatible with C++11. They intended to be fully compatible, but every time you give a spec that's compatible to a committee, they will improve it, and they did a little, so it's mostly compatible, but still smaller than C++98. In the middle of the decade, last decade, we added TR1, the first set of standard library extensions, which expanded the library side of the story by quite a bit, maybe 25% or so. And nearly all of that was then added and more in C++11. The language grew quite a bit. We covered many of the highlights today, so significant growth to the language, but even more growth to the standard library. So today, this is roughly the size of portable C++. How does this compare to other languages that are popular and common? For example, if you were to, by scale, by word count, and I did this, count the number of words in the C++11 specification for the language and the C# specification, about how big is the C# box, roughly? half, 1/10, even K&R wasn't 1/10, but. So quite a bit smaller. Well, if you do the work, and this is actually, the language hasn't changed that much in the last few years. If you take a 2008 snapshot, that is the relative size of C# 3.0 in 2008 by spec word count. I did it. I know. C++11 is not that big. Plus, it gives you many more orthogonal features that go together. But every language does its thing. Everybody has to deal with complexity in the language. And rightly should worry about, do we really need this feature? Can we afford it because of the complexity? What about Java 7 last year? Rough size of the language, not the library, just the language. It's about this. Slightly bigger than the specification for Java 7 languages, slightly more than the word count of the C++11 language, but only a little bit. So these languages are very comparable. They actually have very similar sets of features. Some are more powerful and oriented to systems programming. Some are oriented more to GC and OO, but they're roughly comparable. But now if you draw their libraries, the standard library that anybody who writes a C# or Java book can be guaranteed will be available to whoever reads his book on every implementation, how big is the library? Now that doesn't quite fit, so let's just pull back a bit and see. We begin with the C# standard libraries. Now how do we define that? The C# standard library I'm going to define is at least the core .NET frameworks that ships with Visual Studio. Now this is not all of the managed libraries that ship with Visual Studio. It is only the core .NET frameworks that ship with Visual Studio. It is only the core .NET frameworks that ship with Visual Studio, including the BCL, the core FX. That's the rough size. Java's library is even bigger. The Java 7 Standard Edition API, counting by number of types, is considerably larger than the .NET FX. But if you go back to C# and say, well, if you include all the managed libraries that ship with Visual Studio Professional, that anybody who writes a book about C# knows will be available to anybody who has VS Pro, that's to scale, roughly, the size of the libraries. Can you see the problem? There is no bigger or more important thing we can do to help standard C++ than to deliver a vastly larger, portable, preferably standard C++ library that we know is available to every developer on every C++ implementation, supported by the vendor, and uses consistent types. Some of you may be thinking, but come on, Herb, you're excluding Boost. Boost is pretty portable. People use it widely. How many of you use Boost? It's probably the most in the room, it's probably the most widely used library. Boost, at its core, if you look at the core stuff like file systems, smart pointers, networking, that's good. The rest of it kind of got off in the weeds. So since the quote that's on their page from Andre and me, we were talking about the core part that really is broadly applicable and is really nice and useful. But Boost is actually, it's good. Let me not say anything bad about it at all. It is good. But it is not the solution. In fact, it is a symptom of the problem. It is not a solution, it is part of the problem. People use Boost because they don't have anything else. And they have a few others. We have a few others like Poco, and everybody has their own libraries internally like Adobe and Microsoft and Google. Everybody has their own. But when you go to a new C++ developer and they say, how do I do XML in C++, what do they say? You say, C++ is the world's best language for library building, which is true. You can find several good XML libraries. Just find one that works on your platform and pick it. That is not an answer. Because the next question is going to be, well, I need now a library for JSON, or I need a library for REST APIs. Oh, we have lots of good C++ libraries, and many are available. Pick one of the ones that's available for your platform. Oh, by the way, its types don't work with the types of the XML types. Even Boost inside itself has multiple redundant types that aren't the same in different libraries because it's a collection of libraries that are not always well integrated. One of the benefits of having a large standard library is consistency and that you know it's going to be available. Bjarne has been talking about this for many years. Like he said yesterday, he should have shipped, he feels, C++ with a bad library instead of with no library initially. And since then, we've always been looking for more libraries. He mentioned this 4 years ago in his Hopple 3 paper. He was pushing us through OX to be ambitious and opportunistic. Please bring more libraries. And said, well, at least we're going to roughly double it. And that is not nearly enough. So the goals we should set for ourselves, I feel, over the coming few years, is to have a large set of useful and current libraries that are available on all major platforms. Boost is okay so far, but here's where we leave them behind. That is shipped with and supported by C++ implementations, and that's composable using consistent types. I would be happy if it were de facto available. And you could just write a C++ book knowing, yeah, there's this thing, it's not standard, but everybody has it, everybody ships it, it's as good as standard. I'd be happy with that. I would be far happier if it were actually de jure standard and approved by WG21. So this is wonderful. Wouldn't it be great if we had all these standard libraries? Wouldn't it be great? So wonderful idea. But once the pipe dream goes by, where do we find these things? Well, in the standards committee, we have, at our last meeting in Bloomington, we opened the door and we publicly said, and I reported this on my blog post, the door is open to library extensions. We did the same thing at the beginning of OX, and then you wait, and a trickle comes in. And it's mostly low-level libraries, very, very small. Some good ones like hash tables, but not XML, not JSON, not these high-level things. These libraries exist. Poco has them, Qt has them, Boost has some of them, Microsoft has them internally in Windows. Microsoft Office already has portable libraries internally that work on Mac and Windows, have for years because they've long supported Mac as an operating system. Facebook has them. Google has them. What we need to do is pry them out and actually invest the time and effort to submit them for standardization. And so what we've just begun to do, and I'm trying to organize an effort that we're calling Pickle, a portable C++ library. We've already reached out and have good input and help from friends who are on the committee at Google and at Apple, and we're going to reach out for even more to say, let's find the libraries we all have, including internally at Microsoft, and submit them. And we don't care if it's ours that gets standardized. We should all offer, organize among ourselves which one we think is best for a particular thing, get these things covered, and it doesn't matter whose gets picked, it matters that there be one that we can all conform to, that we can deliver, that everybody 5 years from now will just be able to take for granted in C++. So we're just getting this started, and very happy to say that in the pre-Kona mailing, so we will be discussing starting on Monday, several of these already. Google has made some submissions, Microsoft has made some submissions, coordinated to make sure we don't overlap and we pick who's got the best thing. Okay, let's submit that. Let's pry them out and submit them. We did that a little bit with Boost last time, and we need to do this in an organized way or it won't get done. This really requires an investment of time and energy that you probably may not appreciate, because this is all done by volunteers. How many of you have actually proposed something, small or large, for ISO C++? There's a few in the room. Can you keep your hands up and just wave a bit? Okay, there's a few in the room. One of the reasons it's so few is because it's a huge bar. You have to write an initial proposal paper, shop it around. You actually have to physically go to the meeting, be present during discussion, defend it, take feedback. Hopefully they will like your proposal enough to give you feedback and say, you know, I think it's a good idea. Please come back next time with another version of the proposal changed in the following ways. So you go off, do another 6 months of work, come back to the next meeting. They'll give you further feedback. This is the best case, not that they lost interest. They give you more feedback, sometimes to go back to, no, you were right the first time, please can you change it back again? And it usually, not making this up, it's how it goes. And this is part of the consensus process. It is very time intensive and labor intensive, and that's why nothing gets done unless somebody says, let's solve this problem. So we're gonna see how we do. Maybe a year from now we'll say, we tried and we didn't do better, but I really think we need to try to solve this problem, and it's going to require people from Google, Apple, Microsoft, Boost, Poco, across the industry to invest considerable time to say, let's make sure we have these things. So in terms of scope, I would set out the following, the do's and don'ts. Do focus on pure libraries. We want to see what we can do with the existing C++11 standard and use all of it. Assume all of it exists on the compiler, and let's design our library in a modern way based on that. Do focus on common modern tasks that actually have existing practice. So it's not an inventive library. We know it's going to work. We're not trying to advance the state of the art. Message queues, ranges, parallel algorithms, networking, file system, async. Half of those are being proposed at this coming meeting. Are you excited by this list? Really? I'm not hearing it. But wait, I don't blame you because I'm not interested in this list very much myself. This is what we ought to have had the last decade. Okay, this is catch-up. Low-level libraries, if all you say is give us libraries, this is what people come with. They come with these low-level libraries, which is fine. But what we need even more is the REST web services, sensor fusion, HTTP, text messaging, audio, image, video, databases, crypto, XML, JSON, XSLT, persistence, setting preferences, compression. Please, in a standard way. This is what we need. Would you like to see a standard library that includes even half of these things? We don't want things that target niche uses. We do not want to become a platform in our own right. And we don't want to try to develop something that pretends to be cross-platform, but is inferior to native everywhere. The canonical example is a GUI WIMP toolkit. That's not the kind of thing that I think would get traction in standardization, nor would be appropriate. But thin layers over existing services so they let you write portable code over what operating systems and environments already have. That would be a big deal. So we talked about C++11 as a new language, the adoption scorecard, and what's next. Let me give you a short taste of what's next today, then we'll break before our next talk. In 15 minutes, we'll hear from one of the lead developers of the Clang compiler at Google that we invited, Chandler Carruth, to talk about Clang. Because Microsoft doesn't currently use Clang. We don't have any plans to. Clang doesn't target Windows very well. But Clang is important. You should know about it. You want to know about it, so we wanted to make sure we had content about it, because Clang is one of the key examples of the investment across the industry in C++. When's the last time there was a new C++ compiler being heavily invested in by the largest tech companies in the world? Let's find out more about that in 15 minutes. Next, after lunch, is the static if talk I mentioned that we invited Andre to come give. And then Bjarne will take the stage one more time along with his colleague Andrew to talk about a concept design. Because even though it's not in the near term for C++, we're now in the afternoon going forward looking. And a lot of people are interested in concepts, and rightly so. So we felt it was important to include a status update. And then we'll have a panel at the end of the day where feel free to ask me about anything I just talked about that any of the speakers have said and more. And that's how we'll cap off the day. Thank you for coming. Now let's take 15 minutes and grab coffee quick. We'll be back and we'll talk about the Clang compiler and what Google is doing.